Welcome, scholars, to Mr. Honeycutt's math class. For this video, we are learning how to determine x-intercepts graphically and algebraically from factored form. Okay, x-intercepts, again, it's when it intersects the x-axis. So you can have multiples of them, and that's when the function is outputting a zero. Okay, there's different kinds of polynomials. You can actually have two kinds of x-intercepts that are called like the bounce, and the cross is like, I mean, nobody really calls them that, but this is this one, when it crosses the x-axis, the polynomial root is going to have an odd power. So you'll have like some sort of factor like x minus c. Okay, and when it bounces, it's going to have some sort of even power. Okay, because a negative times a negative is a positive. So if you have a double root, this is sometimes called a double root, and this is like a single or a triple root or something like that. So this distinction is actually super important in calculus. So that's why I'm bringing it up here, just to kind of make you aware. But there are double roots with bounces, and there are single or odd number of roots there where they cross the line. And the sign does not change on the bounces. Notice this is negative to negative, and then this goes from negative to positive. It's going to come in handy next lesson. So checkpoints. So we're looking at x-intercepts. So where are the x-intercepts? Hey, I got one here. All right, I got one here. I've got one here, and I've got one here. What x values is just so my x-intercepts, though I've got an x-intercept, I've got x equals -4, -1, +1, and 5. Then at what x values does f of x change sign? Well, x changes sign at -4, -1, 1, but not at 5. Okay. So notice it goes from negative to positive here, it goes from positive to negative here, negative to positive here, but here it goes from positive to positive. So it does not change sign here because these are crosses and this is a bounce. Okay. Algebraically, what's happening, as I mentioned earlier, it's the x-intercepts when the function is outputting a 0. Okay, so like when does sine x equal 0? So if we've forgotten, we could just, hey, sketch a little unit circle. Sine is my y, so that happens here and here. So when does sine equal 0? Well, that's when x is equal, from like -pi, 0, pi, 2 pi, etc. And when's cosine equal to 0? Well, cosine's equal to 0. I'll do that in green, I guess. Here and here. So that's when x is equal to pi over 2, 3 pi over 2, 5 pi over 2, etc. We could have started earlier and said, hey, x is equal to, -pi over 2, so on and so forth. Now, if you remember what the exponential graph looks like, it looks something like this. Like very not great exponential. So when does it equal 0? Well, remember, it never actually touches 0. There is an end behavior where you could say, hey, the limit as x approaches -infinity of 2 to the x equals 0. Okay, but it never actually gets there. So it's just, this is how a way to talk about what's happening on the left end of the function. So this exponential, it never actually hits 0. So moving along. So hey, again, looking at the x-intercepts of sine, like, hey, look right about there and right about there. Hey, it's a little more than 3. I'm going to bet it's going to be about 3.1415. Remember that this is what the sine function looks like. Looks like a wave. You're going to have to memorize a bunch of these functions if you haven't started working on that already. So then this would also be like 6.28 This would be the -3.14. See how that works? So, and then there, of course, is the 0. All right, so this is an x-intercept, 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 x-intercept. Now, the zero product property. It's funny, my son the other day asked me this really long math problem where he was like, well, what's you know, 1,000,000 times 1,000,000,000 times 7 times 35 times 8 times. And honestly, after about 12 numbers, I started passing out. And then and then I was like, all right, son, I don't know. I'd have to get it out of calculator. He's like, well, weren't you paying attention, Dad? I said 0 times 0 in the middle. Like, and so then it would just be 0. And I was like, all right, that's actually pretty clever. But that is true. If you have anything times 0, anything times 0 is 0. This property has some interesting graphical features to it. So this zero product property is a huge part of what makes 0 so helpful and what makes X-intercepts so helpful. What that means when it comes to functions is that we can break, if there's a 0, we can often, not always, but oftentimes break functions into smaller multiples of 2 functions and then find those functions individually. So if a function can be broken into smaller functions that are being multiplied, and one of them is, and f of x in this case is 0, then either p of x has to be 0 or q of x has to be 0. Now that's really abstract, but you've actually seen this many, many times before. We called it factoring. Okay? So that when we factor this function, x squared minus 3x minus 10, okay, you can factor it here and factor it here. Well, when x minus 5 is equal to 0, what is that? So when x minus 5 is equal to 0, hey, solving x equals 5. Hey, look at that. Oh, there's an x-intercept. All right, what about the x plus 2? Well, I could also set the x plus 2 equal to 0, and hey, x equals negative 2. Hey, look at that. There's another one. And in fact, what we can do is notice here is your x plus 2 line right here. Here is your x minus 5 line right here. Notice it shares the same intercepts with the function with this x squared minus 3x minus 10, which is this guy. Hey, look, it's a y-intercept of negative 10, right? So it shares the same. So you literally are taking these two linear functions and multiplying them by each other. And when one of them is 0, then the whole graph, the whole function is 0 and has an x-intercept there. So again, the zero product property ends up being very handy, and it means that we can break apart larger functions into smaller parts, which makes them far more manageable. And believe it or not, like the encryption properties of your computer are actually based upon all of this factoring stuff. So there's surprising amounts of uses to that. But yeah, this is the reason why the intercepts and zeros are so helpful, because often it's easier to find that 0 intercept than almost any other, precisely because when we're looking for a 0, when we're looking for an x-intercept, you can break the function up at that part. Notice that the zero product property doesn't work any other time on the function, because there's no other number like 0 where anything times 0 is 0. So that's why it's so helpful to find x-intercepts, because they're often the easiest things to find. And what's nice, and in fact, we can quickly build mathematical models of something by simply knowing the x-intercepts. We really can. We can learn more about we're going to learn more about how to do that next class. But this is where we're going with some of the zero stuff. So what causes x-intercepts to graphically? Well, we're either outputting a 0 or we're multiplying something by 0. Outputting or multiplying by 0.